We've been talking chapter 9, I think. We started talking about stoichiometry. And remember, there's kind of two types of stoichiometry problems we talked about. There's kind of a basic stoichiometry problem. And really, all basic stoichiometry problems are really problems where you're just given one piece of information about somebody in the equation. And they really do follow really four basic steps. You want to balance the equation. You want to convert to moles. And again, usually you want to get it to grams and go from grams to moles using the molar mass from the periodic table. You want to do really the stoichiometry part, which is the mole to mole relationship. And lastly, you want to take those moles to some other unit. Maybe they do want the answer in moles, so you'd be done, or very commonly on the back end of the calculation there, you will use the molar mass from the periodic table one more time. Now, there are also limiting reagent type problems that we talked about towards the end last time. And the idea of limiting reagents and excess reagents is basically the idea that in a chemical reaction, there will always be one reagent that gets used up first, and the other one you have plenty of. You have so much of the other one, you basically have it's still left over when the reaction's done. So I don't know if you guys did the experiment or not, but when you dumped the lead to nitrate solution into the solid and dissolved it, you had some excess amount of reagent left over. Now, when we do limiting reagent problems, as we talked about, there's really kind of a few different ways that you can solve it. The way that we talked about was really based off of this method here that we were using for basic stoichiometry problems. And one of the key things that allows you to know that it is a limiting reagent problem is you're given enough information about your reactants that you're able to get to moles of basically all the reactants. So if you're able to convert things to moles for all the reactants that are present, that's definitely a limiting reagent problem, and you have to take a step. So in a limiting reagent problem, right around here, after we convert everybody to moles, we do just a really basic sort of calculation to figure out if I wanted to use up all of one of my reactant, how much the other one would have to put in there. So basically the idea here, for example, if we had this equation, if I want to use up all of A, how much B is needed? And so, for example, we'll just put some coefficients here. So if we had something like that, we would start with the starting amount, say, of A, just make up 5. We would do our mole to mole relationship here, 2 moles of A and 2 moles of B. That gives that away, and that says that I need 5 moles of B. So somewhere in step 2, I would have known my starting amount of A. I also perhaps say, let's know my starting amount of B. I would compare those two and basically see if I have enough, the starting amount of that reagent to how much is needed. If I do have enough, then that means reagent, excess reagent. If I do not have enough, like in this example here, I would have needed 5 to use it all up. I only have 2 to start with. Then that would mean it would be the limiting reagent. So once you determine the limiting reagent, really important because it is the limiting reagent that always determines how much product you can make. So you cannot make any more product once the limiting reagent is used up. So in this example, B would be the limiting as I do not have enough. This is what I started with. And what I would want to do is use B and then continue on with my calculation here, go from my limiting reagent to the product, and again, convert our moles. The other major way that people usually will do this is, as I mentioned, if you had, say, your starting amount of A and your starting amount here of B in this example, you would just do 2 separate stoichiometry calculations following these 4 steps and figure out how much of the product would be made in this case. And whichever one makes the least amount of product is both your theoretical yield and also your, so that is an alternative approach if you want to do it that way. It's basically just 2 separate calculations, and whichever one's the smallest is both the limiting and your theoretical yield. We also talked about that you could calculate how much of the excess reagent is left over as well in these type of problems. Any questions on those? All right, so why don't we actually try one here, or why don't you give one a go? Maybe there's one. There we go. We'll try this one here. Let's say we did this reaction, a little iron plus some sulfur, make some iron 2 sulfide, and we start with 6.83 grams of iron, and it reacts with 9.34 grams of sulfur. So sulfur is 3207 on the periodic table. Iron is still 5585, I hope. Yeah, 5585. All right, so why don't you follow those steps here, figure out which one's the limiting reagent, and also figure out how much product is formed. So follow those steps, figure out the limiting reagent, and then continue on with the calculation. Okay, let's take a look, see how you're doing. So first couple of things when we read this, we got 6.83 grams of iron reacting with 9.34 grams of sulfur. That basically is both of our reactants in grams, which means we definitely could get the moles for both of them. So that is the big hint that this is a limiting reagent problem. They clearly won't always say, hey, what's the limiting reagent? So that's the big hint that this is this type of problem. We really want to start out like normal, so it doesn't really matter really what approach you take. They're all basically the same. We got to balance the equation, which in this case, it actually is balanced. So we're good on that. Next thing we want to do is convert whatever they gave us into grams, which we do need to do. So we're going to do that for both reagents here. So we'll take 6.83 grams of iron using the molar mass from the periodic table of iron, which is our 5585 grams per mole. Gets you 6.83 divided by 5585. And we'll go with 0.12229. I'm not going to round too much here. We're going to do the same thing there for our other one. So we got 9.34 grams of sulfur, 3207 grams per mole for our sulfur from the periodic table. 9.34 divided by 3207, getting us 0.29124 moles of sulfur. So we balance equation, we convert it to moles. We recognize that this is a limiting reagent type problem. So we do want to do our calculation to figure out the limiting reagent. So remember that you really could grab either of the reactants, it doesn't matter. And you're just going to do a calculation to figure out, do you have enough of one reactant to use up the other? So you could kind of think of these numbers here as our starting amounts for each of these. So if I want to use up all of my iron to get used up, how much sulfur is needed is what I'm going to do here. So that is just a really sort of straightforward calculation. 0.12229 moles of iron. The relationship between iron and sulfur from the periodic table is a 1-to-1 relationship, which means we will use that. 1 mole of iron from the equation gives us 1 mole of sulfur. The moles of iron will cancel, and that gives us 0.12229 moles of sulfur is needed. Once again, that calculation is going to help us determine which one's the limiting reagent and which one's the excess reagent. In this case, we do need 0.122 moles of sulfur. In terms of sulfur, I'm starting with 0.29124. Do I have enough sulfur in this case? I do have enough sulfur. That means that sulfur is the excess reagent and the iron would be the limiting. So I do have enough. That means that sulfur is the excess reagent. And in this example, iron would be the limiting by default. Any question on that calculation? Once I determine which one's my limiting reagent, I want to make sure that I go back and use the starting amount of that limiting reagent to actually calculate the product. And again, our starting amount of the limiting reagent here is that number. So we will now pick up really with our basic stoichiometry steps, just like normal. We'll start with our starting amount of our limiting reagent. Again, that's our limiting. We're now going to do the relationship between our limiting reagent and the product, which also happens to be a one-to-one relationship here. That makes it pretty simple. 1 mole of iron gives us 1 mole of our product. The moles of iron will cancel, giving us 0.12229 moles of our product. This technically would be our theoretical yield in moles. But we're not interested in moles. We are interested in how many grams. So we do need to do the 4th step, which is convert our moles into grams in this case. So we do need the molar mass of these two guys added together. So FES would be 3207 plus 5585, going to give us 8792. And our final step here would be to use that molar mass of 8792 grams per mole to figure out our theoretical yield in grams, which would be 0.12229. Looks like 10.6 grams of FES would be produced here. And once again, that would be our theoretical yield, obviously in grams. Question on that there. Now, we also talked about that you could figure out how much of your excess reagent is left over. So if we wanted to do that in this case, we happen to have picked correctly here. We picked how much of our excess reagent we need, and we know how much of our excess reagent we started with. So to figure out how much of that excess reagent would be left over, we could do a very simple calculation here. We would take the moles of the excess reagent that we started with. We would subtract it from the moles that we needed, which was 0.12229 moles of sulfur. That is going to give us 0.29124 minus 0.12229. 0.16895 moles of sulfur that's left over. And if we want to know how many grams that would be, we can multiply by the molar mass of sulfur from the periodic table. Moles will cancel, times it by 3207, about 5.42 grams left over. We started with 9.34 grams of sulfur. We have about 5.4 grams left over, which means in this reaction, and we use just under 4 grams here of the sulfur. Technically speaking, how much of the iron should be left over? 0, right? Because it's a limiting reagent, so it should be used up. It should be completely gone. Any questions on any of those steps there? Okay. All right, so why don't you try another one here and see. All right, let's try this one here. Uh-huh. 622.7 grams of NH3. That is the molar mass there, grams per mole, 1703. And 1,241 grams of CO2, be a small CO2, 4401 grams per mole. Which of the two reactants is limiting? Calculate the mass in grams of our product. Also given to you here, so you don't have to look it up on the periodic table, so that's nice. How much of the excess reagent will be left over? All All right, so take a few minutes here, see what you come up with. Okay, let's look and see how you're doing here. So in this particular problem, we're given 622 grams there of NH3, 1,241 grams of CO2. So once again, without all the extra words that ask you about the limiting reagent and all those things, you should know it's a limiting reagent problem because you do have enough information to get to moles for each of those reactants. So again, that is the key. And probably most times they will not tell you it's a limiting reagent sort of problem. So we're going to really, again, follow kind of the basic steps here. We have an equation and it is balanced. We're going to convert everybody into moles. So from the periodic table, you got 1703, which they gave us for our NH3. And for our CO2, the molar mass there is 4401 grams per mole, which they also gave us. If they didn't give it to you, obviously you would go to the periodic table there and add up all the parts to do that. We'll take our 622 divided by 1703. We'll get something like, we'll call it 36.565 moles of NH3. We're going to do the same thing there for our CO2. So take the 1241 divided by 4401. Going to give us 28.198 moles of CO2. So because it is a limiting reagent problem, we once again just need to do that little calculation to help us figure out which one of these two are the limiting reagent. So in this case here, I'm going to want to use up all of my NH3. I want to know how much CO2 is needed. So taking the starting amount, which is what both of these numbers represent, I'm going to take the starting amount of my NH3, which is 36.565 moles. Based on the equation, it is a 2-to-1 relationship between those two. Remember, the mole-to-mole relationship is just the coefficient from the equation. So that is where we get that relationship from. We want to get rid of the NH3, so we're going to put 2 moles of NH3 from the equation. On the bottom, 1 mole of CO2 from the equation up on top. That's going to give us 36,565 divided by 2. Going to give us about 18.283 moles of CO2 are needed to do that. Any question on that calculation there? The purpose of this calculation is to use that number, and now we want to compare it to the starting amount of CO2. So I'm going to need 18 moles, and I got 28. So once again, I do have enough of the CO2. And because I have enough, that means that the CO2 is our excess reagent. So I do have enough. And once again, that tells me CO2 is the excess. And as we talked about last time, by default, the other reactant will be our limiting reagent. So you don't have to actually go back and do the second calculation or anything like that. We know for sure that that guy's going to be the limiting. Any questions on that? Now that we got the whole limiting reagent sort of thing out of the way, we're going to go back. And once again, we want to use the starting amount of our limiting reagent, which is NH3 in this case, and figure out how much product we're going to make. So we'll take our 36.565 moles of NH3. We now want to do the mole-to-mole relationship between NH3 and our product. And it is also a 2-to-1 relationship. 2 moles of NH3, 1 mole of our product here, based on the coefficients. Using the coefficients to help us out here, we will go with 2 moles of NH3 on the bottom and 1 mole of our product up there on top. Basically, we're going to divide that number by 2, so 36,565 divided by 2. Going to give us 18.283 moles of our product. That technically would be our theoretical yield in moles, but we are looking for grams. So we're going to use the molar mass, which in this particular problem was given to us. And again, if it wasn't given to you, you would have to go to the periodic table to add up all the parts. So doing the last step here, that is going to be, looks like 60.06 grams per mole of our product, which is the molar mass from the periodic table. Those guys will cancel. Gets us about 1,098 grams of our product here in terms of sig figs. Actually, not too bad since everybody else was 4, I believe, in there. So we can actually leave it here. This again would be our theoretical yield. Question on that there. Once again, I think it also asks for how much of the excess reagents left over. So again, here we actually chose kind of correctly. We can take the amount that was needed. We could take the amount of the excess that we started with and subtract the two. So our excess left over in this case, we started with 28.198 moles of CO2. Started with that. We needed 18.283 moles. It's needed. Tells us that at the end of this reaction, we should have about 9.915 moles of CO2 left over. And we can use the molar mass that was provided to us as well, which is 4401 grams per mole for CO2. If we want to know how many grams that would represent, and it would represent about 436.4. And we started with, again, about 1,200 grams of CO2. So we still had a good amount of grams of that left over when the reaction's done. Any questions on any of those steps? So again, it really is basically the same 4 steps. You just got to kind of do that additional sort of calculation halfway through to figure out your limiting reagent. Any questions on that there? Okay. So we've been alluding and talking about yields of reaction. There's really sort of 3 types of yields that we come across in a reaction. One is the theoretical yield. And by the way, if it is a yield, it needs to be a product. So reactants aren't yields. So only products give you yields. And again, the theoretical yield is based on the limiting reagent in the reaction. So the theoretical yield is the amount of product that you should produce in a reaction based on the balanced equation and how much you're starting with of the limiting reagent. It should really be your maximum yield. So, you know, whatever you weighed out, for example, to do that last experiment in the solid was your starting amount, and that would give you your theoretical yield. The actual yield is pretty much what it sounds like. It is actually the amount of product that you made when you did the experiment. So obviously in the lab, that would be how much you made as a result of the experiment. In book problems, that is typically given to you. So usually that is given to you in book problems. And the theoretical yield and the actual yield is useful because that will allow us to calculate what is commonly referred to as the percent yield. And the percent yield is to take the actual yield divided by the theoretical times 100%. Now, when you're dealing with percent yield, you want a high number. You typically don't want over. If you get over 100%, frankly, you screwed up somewhere probably. Yeah, it's usually the reason why you got over 100%. For example, the experiment the other day, you filtered it through filter paper, and that filter paper is wet. So if you didn't let it completely dry and you reweighed it, you would have a lot more mass that's actually water than your product, and it would get you a greater actual yield than theoretical yield, and you'll get over 100%. Over 100% yield. A lot more water they shouldn't have, but you typically don't want to get over 100% yield, but higher number is good. 95, 96, 97, and 90s. Those are really, really good. A very small number for percent yield is not so good. That means you kind of lost a lot of stuff along the way, which you don't want. Now, how do we get the theoretical yield? Our actual yield, again, the actual is typically given to you in the problem. Theoretically, you typically need to calculate. So why don't you give it a go here in this reaction? We take 2.46 times 10 to the 4 kilograms of TI. Yeah. A yield, because it's really based off of like an equation. When we talk about an equation, the arrow, right? We have our reactants, we have our products, and really the arrow means to yield. So it means that's why we call it a yield, is basically we take those reactants, they come together and they yield these products, and that's how much of the products that you make. That's why a yield should always be a product. It cannot be a reactant. Yep. All right, so why don't you give this a go here and see what you come up with. We take 2.46 times 10 to the 4 kilograms of TiCl4, molar mass from the periodic table, 189.7 grams per mole, and magnesium's molar mass, 24.31 grams per mole. What is the theoretical yield in kilograms? And if we produce 5.42 times 10 to the 3 kilograms of TI, what is the percent yield? It takes a few minutes to do that. Remember, there are 1,000 grams in a kilogram. Yeah. Okay, let's take a look and see how you're doing here. So once again, we got a couple of things going on. We're looking for the percent yield. And once again, our percent yield going to be our actual divided by our theoretical times 100%. In the problem, we were given the actual, which is that number right there. So we do need to figure out the theoretical here. So we need to do a stoichiometry problem. Once again, here we're given actually the starting amounts of both reactants in kilograms, which means we can go to grams and also go to moles for each of them. So this, once again, is a limiting reagent problem because we can get the moles of both of our reactants. So we have an equation. It's balanced, like we want to start all stoichiometry problems. We're going to convert everybody into moles here. So we got one extra conversion to kind of get it into grams and then to moles. So 2.46 times 10 to the 4 kilograms of TiCl4. There is, once again, in a kilogram, 1,000 grams. Now that I have it in grams, I can use the molar mass from the periodic table, which in this case is 189.7 grams per mole. So I'm just adding this sort of extra step to get me to grams so that I could then get the moles, making sure you use your exponent button. We're going to end up here with a number. We'll call it 1.30 times 10 to the 5th moles of TiCl4. We're going to do the exact same calculation here for our magnesium. We're going to take our starting amount in kilograms. We're going to convert our kilograms into grams. And now that I have it in grams, I'm going to use the molar mass of Mg from the periodic table, 2431 grams per mole here. That gives me 1.44 to the 4th times 1,000 and divided by 2431. And that'll get me 5.92 times 10 to the 5th moles of magnesium. Any questions on that so far? So just like we've been doing, I'm just going to grab one of the reactants and again, do a calculation to figure out how much of the other reactant is needed to use it up. So in this case, I'm going to try to figure out how much magnesium is needed. So basically, how much magnesium is needed to use up all of the TiCl4. So starting with my starting amount of TiCl4 from the balanced equation, it is a 1 mole, which is the coefficient, to 2 moles for the coefficient for magnesium. So we're going to use the stoichiometry here to do that. 1 mole of TiCl4 gets me 2 moles of magnesium. The moles of that guy cancels. Gets me 1.3 to the 5th times 2. Gets me 2.6 times 10 to the 5th moles of magnesium is needed in this case. Once again, once I figure out how much is needed of one reagent, I am going to compare it to my starting amount, which are these guys here. So I need 2.6 to the 5th moles of magnesium. I have 5.92 times 10 to the 5th moles of magnesium. Do I have enough in this case? I do. So because I have enough, once again here, that would mean the magnesium would be our excess reagent, and the TiCl4 would be our limiting reagent in this case. Once again, we do need to determine the limiting reagent because that is going to determine how much product we make, which is what we're ultimately after. So we're going to take the starting amount of our limiting reagent and now actually do the calculation to figure out our theoretical yield. So we got moles of TiCl4. We now want the relationship between TiCl4 and our product, which is Ti. And from the equation, it is a 1-to-1 relationship between those two. So that makes it not too bad. A mole of TiCl4, a mole of Ti. Moles of TiCl4 end up, and we end up with 1.3 times 10 to the 5th moles of Ti. Now, that would be technically the theoretical yield in moles. I probably want my end theoretical yield to be in what units? They should probably end up being in kilograms. So everything kind of cancels out correctly. So I'm going to do those two conversions right here. I'm going to use the molar mass from the periodic table for Ti, which would be 4788 grams per mole. Those cancel. And since I want it in kilograms, I'm going to do 1,000 grams in a kilogram just to get me again into the right units here. So taking 1.3 to the 5th times 47.88 divided by 1,000. I feel like I missed a number there. Try that again. 1.3 to the 5th times 47.88 and divided by 1,000 here. That is going to get me here 6.22 times 10 to the 3 kilograms of Ti. That would be my theoretical yield. Any questions up to there? Now that I have the theoretical yield and I have the actual yield that was given to me, I can now calculate the percent yield. Percent yield would be our actual, which I kind of scribbled over, but I think it says 5.42 times 10 to the 3 kilograms divided by our theoretical 6.22 times 10 to the 3 kilograms times 100%. And that's going to give me looks like 87.14%. Not too bad. Percent yield in this case. Yeah. Any questions on any of those steps? Yeah. You could. So you could have done kilograms the whole problem. You just want to make sure you're not off by any type of factor. The other sort of question similar to that is in terms of calculating percent yield, it doesn't necessarily have to be grams and grams. It could be kilograms and kilograms like we did here. You could also calculate the percent yield using moles and moles. So as long as the percent yield calculation, both the theoretical and the actual are in the same units, you could calculate the percent yield. It doesn't necessarily have to be grams. Yeah. 47.8. Are we talking about this number or when I was converting, say it one more time? For the theoretical, this number right here, that's the molar mass of Ti for the periodic table. Yeah. Yeah. Other questions? Yeah. High percent yield means, for lack of a better word, you did the experiment good. There wasn't a lot of side reactions. You didn't lose a lot of product along the way when you did the reaction. And that's usually what you want to go for. Sometimes people hear percent yield and get confused sometimes with percent error. Percent error is, how good or bad you did it. In percent error, you want a really low percent error when you do something. But percent yield, you typically want a high percent yield, not above 100. But it gives you how good sort of the experiment went. And again, if you think about maybe the experiment did the other day, it makes this yellow solid and you stir it with your stirring rod. A lot of the yellow solid stays on your stirring rod, maybe doesn't get back onto the filter paper. A lot of the yellow solid stays over in the beaker, doesn't get onto the filter paper. So those are all places along in a normal sort of process of doing an experiment that, you just lose a certain amount of product based on just doing the actual part of the experiment. In addition to anything that you might have screwed up on, you get a worse percent yield. Other questions? Let's try one more here to wrap it up. All right, we do this reaction here. We start with 100 grams of ammonia, reacts with 100 grams of carbon dioxide, and we produce 120 grams of our product. What is the percent yield? Nitrogen is 1401. Carbon is 12.01. Hydrogen 1.008. Oxygen here 16. By the way, just to help you since we're getting to the end, we did ammonia earlier. Molar mass is 1703 grams per mole. And CO2 is 4401 grams per mole. We used those in previous problems. I think we saw this guy as well, so cut down on a little bit of time. There you go. Okay, let's take a look at this. So once again, we do know that this is a limiting reagent problem because we are given the starting amounts of both our reactants, and that means we can get some moles of each of those. So that's where we're going to start with here. We're going to take the 100 grams of ammonia. We're going to use the molar mass of ammonia from the periodic table, 1703 grams per mole. We're also going to take the 100 grams of CO2, use the molar mass from the periodic table, 4401 grams per mole. That is going to give us 100 divided by 1703, 5.8720 moles of NH3. 100 divided by 4401, 2.2722 moles of CO2. Once again, we're going to do our calculation to figure out which one's the limiting reagent. So I want to know how much CO2 is needed in this case. to basically use up all the NH3. So I'm going to start with my NH3, which is 5.8720 moles. Using the mole to mole relationship from the equation, it's a 2-to-1 relationship. 2 moles of NH3, 1 mole of CO2. Then we're going to divide that by 2. 5.8720 divided by 2 tells us we need 2.936 moles of CO2 is needed. Remember, this is our starting amount. So we're going to compare those two, and we do not have enough. So in this case, that means that the CO2 is the limiting reagent, the NH3 is the excess. So now that we got the limiting reagent figured out, we're going to, I'm just going to get rid of some of this stuff here to write on. Give me one sec here. Get rid of those guys here, a little bit there, a little bit there. Now that we have the limiting reagent, what we're going to do is use the limiting reagent's the starting amount to figure out how much of our product we're going to make. So in this particular case here, we're going to take 2.272 moles of our CO2. We're going to do a mole-to-mole relationship between the CO2, our limiting reagent, and our product, which is a 1-to-1 relationship from the coefficients. 1 mole of CO2 gives us 1 mole of our product here. Those guys are going to cancel, giving us 2.2722 moles of our product. Using the molar mass, which I just erased, was 6006, I believe. We're going to convert that into grams of our product. So using the molar mass of 6006 grams per mole, that's the molar mass of our product here, will get us 2.2722 times 6006, a theoretical yield of 136.5 grams for product here. And that is our theoretical yield. Now, our actual yield was given to us in the problem, which I kind of forgot, which I think was 120 grams. So our actual yield was given to us in the question, which was 120 grams. So to calculate our percent yield, we will take our actual 120 grams divided by our theoretical of 136.5 grams times it by 100%. Gives us a percent yield here of 87.91%. So once again, here to solve these problems, you use our basic stoichiometry steps, or if it's a limiting reagent, our limiting reagent steps to figure out the theoretical yield, and then to calculate the percent yield, take the actual divided by the theoretical times 100%. All right, that should wrap up chapter 9. And we'll wrap it up there for today.